Earth Systems 3209, Unit 4, The Forces Within Earth. References for this unit can be found in your textbook in chapters 4, 15, 16, and 19. Appendix A and Appendix B in the curriculum guide. Unit 4, Topic 5.2. This topic will look at volcanic eruptions and plate boundaries. We'll focus on describing how the characteristics of magma can affect the nature of a volcanic eruption. The factors include silica content, viscosity, and gas content. This lesson will also focus on relating the eruption style of each type of volcano to the associated plate boundaries, and also focus on identifying rocks associated with each type of plate boundary. Let's first look at the nature of volcanic eruptions. What determines if an eruption is violent or gentle? There are three primary factors that affect the eruptiveness of a volcano. One is the magma composition. The more silica you have in magmas, the more viscous or thick the magma will be. Magma's temperature: the hotter a magma, the less viscous or fluid the magma will be. And thirdly, the amount of gas in a magma. The amount of gas can increase the fluidity of the magma. So in a nutshell, magma viscosity, which is magma stiffness, will determine the mobility of the magma. Factors that determine the violence or explosiveness of volcanic eruptions again include composition, temperature, and amount of dissolved gases. The above three factors actually control the viscosity of a given magma, which in turn controls the nature of an eruption. Information on these topics can be found in your text on pages 89 through 95. Let's first look at the most influencing property on the eruptiveness of a magma. Viscosity is the measure of a material's resistance to flowing. Example: the higher the viscosity of materials, the flow will be greatly difficulty. That is, the higher viscosity materials flow with great difficulty. So the more viscous a magma is, the harder it is to flow. For example, molasses. Molasses, when it is cooler temperature, will flow very slowly, and that would have a high viscosity. So let's now look at some of the factors that affect viscosity. Viscosity is influenced mainly by its composition, and the composition relates directly to the amount of silica in the magma. If the silica content is high, the magmas will tend to have a higher viscosity. And for example, felsic lavas, such as rhyolites, these lavas would have a high viscosity because they have a higher silica content. Lower silica content would equal lower viscosity or more fluid-like behavior. Mafic magmas and lavas, such as ones in basalt, would have a low silica content and therefore would be less viscous. Another factor that affects viscosity will be the temperature. The hotter the magmas, the less viscous they are. A mafic magma tends to be hotter, therefore it tends to flow easier, and it will be less viscous. Cooler magmas tend to be more viscous or thicker. Felsic magmas, which tend to be cooler, would end up having a high viscosity. A third factor that affects viscosity would be the amount of dissolved gases. Gas content affects magma's mobility. Gases expand within the magma as it nears the Earth's surface due to the decreasing pressure. The violence of an eruption is related to how easily gases can escape from a magma. In summary, Fluid, low viscous lavas generally produce quiet eruptions, and these eruptions can be found on the ocean floor. Highly viscous lavas, such as rhyolites and andesites, produce more explosive eruptions, and these eruptions are associated with continental crust. Let's look at some of the materials that are extruded from magmas, or from volcanoes. Lava flows are the magma that comes out of the volcano on the Earth's surface. Basaltic lavas are much more fluid, and these basaltic lava flows are termed after the lava flows from Hawaii, and those being Poihoi lava, resembles a twisted ropey texture, and A'a lava, which has a rough, jagged, blocky texture. Also, the amount of dissolved gases would influence the lava flows, and is another material that is extruded from a volcano. 1 to 6% of all magma by weight is made up of dissolved gases. These dissolved gases are mainly water vapor and carbon dioxide. When we look at basaltic lava flows, they generally have a lower silica content. The first basaltic lava flow that's extruded from Hawaii that we will look at is called a Poihoi flow. These flows are thin, broad sheets, and are approximately 10 to 300 meters per hour. They are smooth and wrinkled outer skin with molten flow beneath, and they're basically seen in Hawaii. So Poihoi flows are usually thin and broad sheets, and they flow at approximately 10 to 300 meters per hour. In contrast to a Poihoi flow, a second type of basaltic lava flow would be a A'a flow. These flows are generally thicker and slower, and they flow at approximately 5 to 50 meters per hour. These magmas are characteristically rough and jagged at the surface, and we can see this type of flow behind the two gentlemen walking down the middle of the road. When we look at plate boundary volcanism, volcanoes are associated with 2 of the 3 types of plate boundaries, these being convergent and divergent boundaries. Very little volcanic activity, if any, is seen at transformed fault boundaries. Volcanism associated with plate boundary activity are found in 3 general areas. 1, ridges, which are also known as spreading centers, located beneath the oceans. Number 2, subduction zones, which are located at an ocean-continent boundary. And number 3 will be the interior of tectonic plates. References in your text for these topics can be found on pages 116 to 122. Let's first have a look at the spreading center eruptions, more commonly called a rift eruption. Rift volcanism can occur in 2 areas. The first area will be beneath the oceans at mid-Atlantic ridges, and the second area could be within continental plates, such as the African rift zone. Rift eruptions are associated with divergent plate boundaries. The eruptive style is generally quiet, with free-flowing lavas. This is because the magma or lava has a low silica content and also lowers gas content. These flow relatively low viscosity, and the magmas are known to be fluid. Basaltic magmas are produced at spreading centers, and these produce shield volcanoes, which are formed along ridges when basaltic lava flows onto the ocean floor. Let's now look at and compare with subduction zone eruptions. The subduction zone eruption, these eruptions are associated with convergent plate boundaries. The eruptive style is generally more violent and explosive. This is because the magma and lava has a medium or high silica and gas content and has a relatively higher viscosity. Therefore, the magmas are more thick. Basaltic magmas are produced at ocean-ocean convergent boundaries, whereas andesitic and granitic magmas are produced at ocean-continent convergent boundaries. So subduction eruptions can display both a low viscosity basaltic magma or the higher viscosity andesitic and granitic magmas. Clumps of volcanoes formed along convergent plate boundaries. Some examples include Mount Fuji in Japan and Mount St. Helens in the United States. When we look at subduction zone eruptions, subduction volcanism can occur in two areas. The first area is the ocean-ocean convergent boundary. Ocean crust subducts beneath ocean crust at an ocean-ocean convergent boundary. Basaltic magmas are produced and they burn upward to the surface, forming a chain of volcanoes called a volcanic island arc. And these volcanic islands are parallel to the trench. Some examples include the islands of Japan. So if we look at the diagram to the right, we will notice that we have a volcanic island arc forming where we have ocean waters on the right and on the left. These volcanic islands form a string of volcanoes that travel parallel to the ocean trench. The second type of volcanic eruption that occurs at subduction zones will be an ocean-continent convergent boundary. At ocean-continent convergent boundaries, the ocean crust subducts beneath the continental crust. At these boundaries, andesitic and granitic magmas tend to burn upward into the continental crust, adding to a mountain system. Most of the world's volcanoes are of this type, and they border the Pacific Ocean and are located within a volcanic zone called the Pacific Ring of Fire. Examples of this type of volcanism can be found in the Andes Mountains in South America and also in the Rocky Mountains in North America. So if we look at the diagram to the right, we see we have an ocean plate subducting beneath the continental plate. When it gets down to certain depths, roughly about 100 kilometers, we get melting of the ocean floor, which burns up through the continental crust, melting it in its migration to the surface, therefore mixing basaltic and granitic, producing andesitic magmas at the surface. And these andesitic magmas form a rock called andesite, which is the predominant rock type found in the Andes Mountains. Let's have a look at the nature of volcanic eruptions and compare the different plate boundaries with the different types of volcanoes. In a shield volcano, these volcanoes tend to have the least amount of silica, approximately 50% by composition. Because they have low silica content, they are known as the least viscosity. They are least viscous, they're very fluid magmas, and they also have the least amount of gases. Because of the low viscosity and the low amount of gases, they generally erupt in a quiet, free-flowing lava, and their predominant eruption style is found at divergent boundaries. So shield volcanoes are predominant at divergent boundaries. The second type of volcano would be an ash and cinder volcano. Ash and cinder volcanoes have the greatest amount of silica content, generally over 70% of the magma by composition. They have the greatest viscosity, and they have the greatest gas content. Therefore, because they have a great viscosity and a great amount of gases within the magmas, they tend to erupt violently and explosive, ejecting pyroclastic material to the surface. These type of volcanoes are found at convergent, and some can be found at divergent. So ash and cinder cones are predominant along convergent and divergent boundaries. The third type of volcano would be your composite volcano. Composite volcanoes have intermediate silica content and intermediate gas content. Therefore, because they have a higher percentage of silica and viscosity, their gas content is intermediate. Therefore, they tend to erupt with alternating quiet, free-flowing lavas and also violent and explosive pyroclastic material. So in an eruption along a composite cone, we tend to see alternating lava flows with pyroclastic material. And these type of volcanoes are predominant at convergent plate boundaries. Let's look at some examples from past exams. First question reads, which rock type is associated with divergent plate boundaries? Because divergent plate boundaries are located on the ocean floor for the most part, they generally are made up of a rock called basalt. And basalt is the main rock type found in the ocean floor. So the rock type that's associated with a divergent plate boundary will be C, basalt. Second question. Which type of volcanic cone displays gentle, fluid, mafic eruptions? So if we're looking for a gentle, fluid, mafic eruption, gentle and fluid would suggest it has low silica content and low viscosity, and a mafic eruption would suggest it's associated with the ocean floor. So the volcanoes that we find that erupt gently with a fluid, mafic, basaltic lava, that would be a shield cone. So our answer to the second question would be C, shield cone. Example number 2 reads, which landform at location X and rock type at location Y is shown in the diagram below? If we look at location X, we see that we have water on both sides of the volcanic feature. And this volcanic feature will be an island arc. So volcanic island arcs are located on the ocean floor directly above a subduction zone where we have ocean floor melting. Therefore, the type of rock that you would find at Y would be basalt. So our answer to this question, what rock form do you find with the diagram below, is associated with a subduction zone, an ocean-ocean subduction zone. You would see volcanic island arcs, and the rock type would be basalt. Your turn. Take the time now and complete the following question. You can pause your recording while you prepare your answer and compare it with the answer on the following slide. The question reads, describe a spreading center and briefly describe what volcanic activity is present at these locations. So by reading the problem carefully, you need to just make a description of what a spreading center is, and then describe the volcanic activity you would find at a spreading center. So your answer should include the following points. A divergent boundary, sometimes referred to as a spreading center, displays tensional forces caused by mantle convection, causing ocean plates to move apart. So this sentence describes what happens at a spreading center. Basaltic magmas, which are very fluid magmas with little dissolved gases, erupt quietly onto the ocean floor, adding to the diverging oceanic plates. New sea floor is formed at spreading centers. So the second sentence would describe the volcanic activity that occurs at a spreading center. So that would include the 2 points that are asked in the question. Let's review the points covered in this presentation. The nature of volcanic eruptions will depend on 3 factors. Number 1, the composition of the magma, mainly the silica content present. If there is high silica content present, the volcanic eruption will be violent because the magmas have a high viscosity. They're very thick. If the silica content is low, the volcanic eruption will be gentle because the magmas have a low viscosity and are generally fluid. The second condition factor that affects a volcanic eruption will be the temperature of the magma. If magma temperatures are extremely high, they tend to erupt gently, and this is predominant in mafic magmas that are found associated with the ocean floor, and they erupt as shield volcanoes. Cooler temperatures are seen at continental boundaries, where the volcanic eruptions tend to be more explosive and violent. This is because the colder magmas tend to be more thicker and have a higher viscosity. And as the magmas come towards the surface, the gas content will actually bubble out and be released, which contribute to the explosiveness of the volcano. And the third factor that affects the volcanic eruption will depend upon the amount of dissolved gases in the magma. If the magma has a lot of dissolved gases, they tend to be more explosive. If the magma has less dissolved gases, they tend to erupt more gently. The second point covered will be the volcanic activity associated with the two plate boundaries. We noted that very little volcanic activity is associated with transform boundaries, but we do see much volcanic activity associated with divergent boundaries and convergent boundaries. At a divergent boundary, we tend to see more gentle, free-flowing lavas because of the low silica content, high temperatures, and little gases dissolved in the magma. And this is characteristic of mafic magmas that flow out of the ocean floor at divergent boundaries, and also hotspots. These tend to form broad volcanic cones called shield volcanoes. In comparison, at a convergent boundary, we tend to see more explosive volcanoes. These volcanoes are more explosive because they have a high silica content, and they're generally cooler in temperature, and they have a lot of dissolved gases within the magmas. These volcanic eruptions are associated with composite cones that are located within the mountainous regions of ocean-continent convergent plate boundaries. So these points outline the topics that were discussed in this presentation.